So, who of you saw the talk about politicians speak this morning? Nobody. Okay. Yeah, it wasn't German, so maybe. Yeah, I wanted to respond something to the people who did, but yeah, apparently now talking gibberish in human understandable language is, you didn't hear about that today, but talking gibberish in electronic languages, you are probably familiar with that. So Ben here is a security researcher with Checkpoint, and he will talk to you today about DGAs, so algorithms that produce gibberish, but they got a bit smarter in the past, and he will tell you something about how to detect gibberish, which some people might want to have for politicians too, but you have to use reason for that, and he will give you an idea about how you can do that for DGAs. Okay, give a warm round of applause for Ben here, and let's begin.
Is this thing on? Oh, it is. Okay, first things first. If this slide makes any amount of sense to you, then I'm sorry to have to tell you this, but you're probably a robot. Well, the good news, that's the bad news. The good news is that you've come to the right lecture, because once this is done, you'll be able to detect gibberish just like the rest of the humans. You'll be able to blend in, and no one will know a thing. So first, I'm going to refresh your memory a bit about what DGA is and what the problem is that it was trying to solve. Let's look at a regular scenario, a basic scenario where an infected system has been infected with malware, and it wants to converse with its command and control server. That's what malware does nowadays. In the past, it may have just done its own thing without receiving any commands, but today, malware usually waits for commands and operates based on commands that it receives. So, in this basic usual scenario, the malware came with a built-in DNS address. It's hard-coded, and the malware queries the DNS server with this hard-coded address and receives a response. This is the IP address of the CNC server. Now the infected system contacts the rest of the internet and the CNC server. The CNC server very excitedly responds, yes, I have another machine under my sway, and the connection is complete. Now the infected system and the CNC server can converse. So all of this is fine and good until one day the powers that be, maybe the authorities, I don't know, they find out about all of this, and they talk to the people in charge of the DNS server. That's probably your ISP, not necessarily. And they tell them, well, there's been this shady activity going on, and it's making use of your DNS servers. Would you kindly make sure that it stops? And the people in charge of the DNS server do not want any trouble. So they remove the record pointing to the IP address of the CNC server. And now the infected system, just as before, makes the DNS query to the DNS server and asks, okay, where's the IP address of my CNC server? And the DNS server basically responds, go fish. Now the CNC server just stands there, fully functional, waiting to send commands, and it stands there and it waits and it waits and it waits, and that's not very good for the campaign. Now, DGA is basically a mechanism that campaign managers came up with. They looked at this problem, the ease with which a DNS takedown can happen, and they said, we want something better that won't be taken down as easily. So I could stand here for a lot of time and talk theoretically about DGA and how it works, but I think a practical walkthrough of just how it works in practice is going to be more productive. So let's see how it actually works. Our story begins with the CNC server, and it has access to a pseudo-random number generator, which is basically a creature that takes in a small amount of entropy, randomness, and outputs a large amount of entropy, randomness. Now, this pseudo-random generator specifically takes in a publicly available seed, such as the date of today, or maybe the headlines of today's newspaper. I don't know. The important thing is that it should be publicly available to everybody. Now it is a customized algorithm that takes in this publicly available small amount of information and outputs a large number of domains. These domains are not very understandable, and this is typical, and this is basically what this lecture is about. But now what the CNC server does is take one of those domains at random, typically that's what it does, and registers it with the DNS server to point at the IP address that's relevant, the IP address that the infected machine can contact. Now, what happens at the infected client side? Something similar. The infected system also has access to the same pseudorandom generator that came bundled with the malware. And it has access to the publicly available seed because it's publicly available. So it consults the pseudorandom generator and asks, what are the domains of today? What are the domains available to me today? And it gets a list of how many domains are there. It varies. Sometimes it's 50, sometimes it's 200. There's a lot. That's what I'm trying to say. And now the infected system knows that the CNC server had registered one of those domains to point at the IP address. But it doesn't know which one. So what is it going to do? There's really only one solution: contact all the addresses. It's going to iterate over all the addresses one by one and make DNS queries asking for the relevant IP address. Now, most of those domains had not been actually registered. So what results is a very peculiar sort of conversation across the DNS protocol that kind of resembles the Cheese Shop sketch by Monty Python. If you're not familiar with it, it's a sketch that involves a guy walking into a cheese shop, and he tries to purchase various kinds of cheese. And as the sketch progresses, it becomes increasingly clear that the shop does not actually hold any kind of cheese at all. The guy asks, do you have any Parmesan? The shop owner says, no. Well, how about brie? No. And so on and so forth. And the DNS conversation going on resembles this exchange greatly. Because what happens is that the infected machine asks the DNS server, well, do you have the IP address for this gibberish address? The DNS server responds, no. Well, how about this gibberish address? No. How about this gibberish address? No, sir, sorry. How about this gibberish address? No, not today, sir. And this goes on and on. Here you can see a traffic capture depicting this process. You can see it repeated, no such name, no such name, no such name. The DNS server says, what do you want from me? I've never heard of any one of those domains. Please stop bothering me. But recall that the CNC server had actually registered one of those domains. One of those domains is a valid domain now that points to the IP address of the CNC server. So eventually, the infected system is going to make the golden query, and the DNS server is going to excitedly jump up and down. Oh my God, I know this one. It reaches down to the drawer and pulls up the IP response. And the infected system is elated. Now it finally has the IP address of the CNC server as before, and it contacts it as before, and all is well with the world. Well, you notice that I kept saying as before, as before, as before. What, all this work just for before, all this bloated mechanism of DGA just to get the same result as before? Well, not exactly, because think what you now have to do if you want to try to take down this infrastructure. Now, suddenly, let's look at the domains generated in one day by this algorithm. That's a lot. And if you're trying to take down this infrastructure and you do not have access to the pseudo-random number generator, the algorithm, basically all of this is random to you. So every day you're going to have to chase down and hunt all of those addresses being queried all over the world. And that's not going to be easy. Now, if a DGA takedown happens at all, here's the more likely scenario of how it's going to play out. First, you have your victim, and your victim gets infected in some, I don't know, enterprise or something, and it contacts the CNC server, and there's data exfiltration and so on going on, and eventually someone wises up to this, and the hot potato gets thrown over to incident response. Now, incident response, they do whatever they can with this. They try to put out this fire, and maybe if we are lucky, they want to draw conclusions from this and make sure that the information that they have obtained is relevant and can be used later to prevent further attacks of this nature by the same family of malware. So if you're lucky, their incident response is buddy-buddy with middle management at some security vendor. So it gets passed over to middle management at some security vendor, which either buries it down somewhere where the sun don't shine, or if you're lucky, it passes, the middle management passes this over to some reverse engineer who is going to spend like a few weeks or maybe a few months poring over this file in IDA Pro until, if you're lucky, this thing results in a report. The report either lies down at the bottom of the internet and no one pays attention to it, but if you're lucky, either a streamlined process or some kind soul is going to take this thing and make sure that the data about how the pseudo-random number generator works is incorporated into a firewall somewhere, which will actually, once this process is done, block any future traffic based on the same domain generation algorithm. See, an easy streamlined process. What could possibly go wrong? But suppose that you had the ability to automatically detect the DGA. Now, you could aggressively cut out a lot of those middlemen. Now, a lot of the links here have better things to do with their time. Middle management, bless their soul, they have better things to do with their time. Reverse engineers too. If you had the ability to automatically detect DGA traffic, you could theoretically put it straight in the firewall. The firewall is going to see the outgoing DGA traffic, and aggressively it's going to shut it down after like 4 or 5 queries and say, I'm sorry, this traffic looks shady, it looks like DGA, you're not getting through. So automatically detecting DGA is useful and it's cool, and as a consequence, there have been past attempts to solve this problem. And we're going to look at some of the past features that have been suggested to identify DGA, and we're going to talk a bit about how those features do not necessarily work 100% well all the time, and how they could be improved, which is what we did. Okay, let's talk about some ways to detect DGA. One way involves looking at character frequency. It's a well-known fact that some letters are more common in the English language than others. So if, let's say, I take the common letters in English and color code them as green, and the borderline letters I color code as yellow, and the rare letters I color code as red, and I take 5 words that I randomly picked out from the dictionary and 5 gibberish segments of comparable length, you can, at a glance, tell which 5 words came from the dictionary and which 5 words didn't. So that's a useful feature. Another useful feature is along the same lines. It's based on frequencies of pairs of letters instead of single letters. Some pairs of consequent letters in English are more common than others. TI is common. XZ is not so common. And another feature is called the longest meaningful substring. It's been suggested in some researches into this problem. It involves looking at your input, your domain name, and seeing what's the longest substring in there that you can actually find in the dictionary. So bug me not contains the words bug and not. So the longest meaningful substring is of length 3. Amazon is actually a word in the dictionary, so this is definitely going to register as not gibberish by this metric. eBay contains the word bay, so it's like 3/4 not gibberish. And this actual gibberish is well gibberish. I can't find any word in the dictionary in this thing. So another useful feature, and the last feature that has been suggested in the past that I want to talk about is the annex domain. Remember, just like the cheese shop, there are the repeated no sir, not today sir, no such name, no such name. Just counting these is a useful feature. So we have all of those suggested useful features for detecting DGA, and we are done, right? The problem is solved and we can go shopping. Well, not exactly, as you might have imagined. The first issue with what I just said is what I like to call the Tumblr Conundrum. I mean, let's look at Reddit. Reddit is like there's the word red and there's the word dit, that's for Morse code, you know, the little dot, for Morse code. And if you look at Google, it contains the words go and, my God, we lucked out. Ogle is a word. So the longest meaningful substring criterion is going to look at Google and say, oh, okay, go, Ogle, seems legit. But let's look at Tumblr. What is a Tumblr? You're not going to find this in the dictionary. I mean, Tumblr is not a word, and no substring of it is a word either. Umblr is not a word. Mblur, not a word. Blur, still not a word either. And so there you have one issue, because the longest meaningful substring criterion is going to look at this and say, this is gibberish. And if you got a human to take a look at this, the human is not going to be so hasty to say that this is gibberish. And we're going to touch later on the reason why. That's one issue. The second issue is Quaijibo. Now, Quaijibo is a DGA engine that surfaced a few years ago. And it draws its name from an incident in an episode of The Simpsons where Bart is playing Scrabble against Homer. And Bart is stuck with the list of letters that you see up there at the top of the slide, and he doesn't know what to do until he says, well, you know what, I'm going to put on the board the word Quaijibo. And he plays that word, and of course it's worth 1 billion points because he used all these letters and on a triple word square and so forth and so on. And Homer is not happy. And he asks Bart, what is this word? And Bart, without blinking an eye, he says, well, Quaijibo, it means a stupid North American yellow ape. So much like Bart was able to pass this under the radar because Quaijibo sounds like a word, even though it's not a word, Quaijibo, the DGA generator, passes domain names under the radar because they sound like words, but they're not words. What Quaijibo does, and this is stupidly simple, it makes sure that every other letter in its output domains is a vowel. Now, you're sitting there and thinking, Ben, look, just this, every other letter is a vowel, and all of the features that you talked about earlier are now suddenly useless? Well, let's look at the letter frequencies. Earlier, the gibberish generated by domain generation algorithms contained lots of rare letters, X's and Z's and J's. Now, if you average out the frequencies of letters you're going to encounter, suddenly it looks much more pitchy because you have vowels everywhere, and vowels are common letters. You're telling me, okay, let's look at the pair of letters, the bigrams. It's the same thing. Pairs of letters with vowels in them are very, very common. Not all of them, but a lot of them. And free letters, you're going to run into more or less the exact same issue. So the letter frequencies approach is now going to be significantly weaker than it was before. And how about the longest meaningful substring? Well, you can play a game and you can look at the domains listed here, which I swear I pulled randomly from a Quaijibo-based DGA, and start looking for words. By skimming this, I found give and nope. And I swear I did not plan this in advance gated, which is very appropriate for this conference. So the point is that now that your features that seemed so strong before, they're now, they're half useful. And if you take half useful features and feed them into a machine learning algorithm, you're going to get a result that's a total loss. So because of all of those problems, okay, let's improvise. Because of all of those problems, we came up with our pretty idea for a solution, a pretty nice theoretical idea that involves looking at the input and deciding how close it is to a concatenation of words from the dictionary. So now Tumblr, that was complete nonsense before, can, with just one edit, turn into Tumblr, which is actually a word from the dictionary. We have a savior here, let's see. Does it work? Oh, excellent. So we inserted just one letter and you got Tumblr, which is a word. Google, 2 edits, and it becomes Google, a word from the dictionary, and that's not a coincidence. This is the word that inspired the company name. Reddit, with 2 edits, becomes Reddit, and now we can finally make sense of those domain names. And as for Quaijibo, Quaijibo generates strings of gibberish, and sometimes it's going to luck out and create a word that's out of the dictionary, but it's not going to successfully create concatenations of actual words. One word might be in there, but not, you're not going to be able to look at the whole thing and make sense of it through the lens of this criterion. So the way forward seems clear. Step 1, we measure the minimum distance of our input from a concatenation of dictionary words, any concatenation, as long as we can reach it. using the criterion of edit distance. I skipped over this, but the edit distance between a word and another word is the minimum amount of insertions of letters, deletions of letters, and edits of letters that you need to get from that word to the other one. So we look at the minimum edit distance between our input and a concatenation of words from the dictionary. And the miracle occurs here, and then we profit because this new criterion is going to defeat Quaijibo and mitigate the Tumblr problem because the word Tumblr is now going to suddenly make sense to us, and we're going to win the day. So we were super happy, and then we actually tried to implement this thing in practice. Why we ran into trouble? Why did we run into trouble? Well, let's look at how you actually perform this, this computation of edit distance. The canonical algorithm to do this is called a flood search. What you basically do is that you take your input and you perform a breadth-first search in the space of possible strings by performing every edit that you can think of. It's basically a stupid brute force. So as the amount of edits that you're willing to search through grows and grows, the size of the space that you're going to search through grows exponentially. If you have an input of size 8, and you're actually willing to search it out exhaustively and see how close to the dictionary it is, then you're going to need to do, I don't remember the number by heart, but it's a large number of lookups. So let's say that one lookup into the dictionary is going to take 1 microsecond. I imagine that's in the right ballpark. So we take the number of lookups, and we multiply it by the number of seconds that we can expect one lookup to take. And now we reach the conclusion that in order to get our answer for how close to the dictionary is the input that we have on our hands, one input, one domain name, we're going to have to simply plug it into the algorithm and sit and wait for 2.5 days. 2.5 days. Oh, by the way, that's a lower bound, the number of lookups that I mentioned earlier. It's not the actual number of lookups. The actual number of lookups is greater. Every calculation you see in this presentation, it's a back-of-the-envelope combinatorics calculation. Yes, it's not exactly precise. It's just to give you an idea. So that was a lower bound. Oh, and by the way, we were implicitly comparing words against a set of all possible concatenations of dictionary words. And there's an infinite number of them. Laptop, paper, concatenation of words, bottle, chair, person, podium, still a concatenation of words. There's an infinite number of them. So the problem is that Google's infinite server project isn't going public in another half a year. So we're not going to be able to take this infinite database and fit it anywhere. So at this point, we realized that we're going to have to improvise. So we needed to come up with some ugly hacks and cut some corners on this insane computation to make it actually feasible to compute this thing. So the first ugly hack that we came up with, it was like a first aid solution, is to use a greedy algorithm. And instead of trying to match the whole input against the set of all possible concatenations of dictionary words, try to look for prefixes of the input and match them against the plain old dictionary. Now, first of all, by using this imprecise approximation, you can expect your running time to drop by a lot because the length of the input that you feed into the the edit distance algorithm has an exponential relation, as I said earlier, to the time you can expect the search to take. So that's first of all. You can see the numbers here, the difference is drastic. But the more important thing is that now we're actually comparing against a finite dictionary, and that's progress. Now, it's not all sunshine and rainbows because the expected time, using the back-of-the-envelope calculation here, is still, what, like an hour and something per one traffic capture. That's unacceptable. It's unacceptable. We're not going to sit there for an hour and wait for the computation on a single traffic capture to go through. So we need more ugly hacks. The second ugly hack involves looking at the classical approach of asymmetric search that I talked about earlier. That's just a stupid breadth-first search. Now, what would happen if I took the dictionary that we have and I bloated it to contain all strings of letters that are within an edit distance of 2 of the original dictionary? What's going to happen? Well, you're going to have a larger dictionary, but the interesting thing that's going to happen is that you will now be able to do a much smaller flood search for the same result. Because think about it. If your input is within an edit distance of 4 of the original dictionary, then it's within an edit distance of 2 within something that's within an edit distance of 2 of the original dictionary. So with just 2 edits, you're going to be able to match up against that something. Now your flood search, the input to your flood search is the same length, but the number of edits that you're expected to make is much smaller. So you cut the exponent, and now suddenly the running time is drastically reduced. But the downside of this is that now your dictionary is larger. Much larger by the back of the envelope calculation here shows like by a factor of 10,000. So it's unwieldy, but we can still live with it. So that's still not enough. Let's go on to the third ugly hack. The third ugly hack is not so ugly actually. It involves looking at the distance measure that we are using. It's the edit distance. Now, what would happen if we disallowed in-place editing of letters? We only allowed insertions and deletions. Now, on the face of it, the metric that you're going to get is not much less legitimate than edit distance. Actually, there's no reason to think that it's less legitimate. It's actually bound within the insertion deletion distance between 2 strings of letters is bound between the edit distance and twice the edit distance. The proof of this is left as an exercise to the reader. And now we switched one criterion for another criterion. And the 2 criterions are more or less, we think, that they're legitimate to the same degree, but now our flood search is going to contain much less options to iterate through because all the in-place edits are gone. You don't have to worry about them anymore. So all of those ugly hacks are nice, but the nice thing really is not the individual ugly hacks, but the way that they come together to form something greater than the sum of its parts. Now, let's look at the symmetric search that I talked about earlier and how it can combine with insertion deletion distance. Let's look at the not a word spooks. We can remove the P and get shooks, and then we can remove the X and get shoo. And if we look at the word shout, we can remove the T and get shao, and we can remove the O and get shoo. And those 2 words, after a fashion, have now met in the middle. So what we have now proved is that the edit distance, the insertion deletion distance between spooks and shout is at most 4, because you can take spooks and remove the P and remove the X. And now you can go backwards and add the O and add the T, and spooks and shout are now connected within 4 edits. Now, there's a peculiar something about this computation. You may have noticed that we didn't have to actually insert any letters. We only deleted letters. So we deleted letters from spooks, and we deleted letters from shout, and eventually we reached this kind of lowest common denominator, and the truth is that it's possible to do this for any 2 inputs. So really we can forget about symmetric insertion deletion and just talk about symmetric deletion. Now, this is a nice thing because now we're only left with deletion out of insertion and deletion and editing that we started with before. Now, let's combine this with the bloated dictionary idea that we saw earlier. We can now keep a dictionary containing all the reduced forms that you can get from a word in the original dictionary by removing letters. So now you can take your input and start deleting letters and comparing against reduced forms, and eventually you're going to be able to meet in the middle, just like spooks and shout did. And the expected time to carry out this computation is much, much lower, because now you don't have the crazy flood search anymore. You only have to delete some letters. Now, to really get this algorithm all the way through, you'd have to look at all the deletions that you can perform on your input, but we decided to limit it to taking away 3 letters, because really the performance gain was very nice from this, and otherwise what word in English you know that you can take away 3 letters and there's still something sensible left of the original? There are some, but we thought that it was a good trade-off. So the limitation that we got out of this was that if actually meeting in the middle requires more deletions than the number of deletions that we were willing to make, we set that to be 3, we won't be able to do the meet in the middle thing. But otherwise, this thing is going to work, and the important thing is that insertions we get for free. All insertions that need to be made in order to get to the word in the dictionary are going to be detected. Even if you need like 8 insertions or something, it's still going to work, because you're going to find the reduced form that you got by deleting those 8 letters from the word in the dictionary. So how good is this thing? How quick is this thing now after we have applied all of those ugly hacks? Well, obviously we need to implement it to find out. I was going to implement it in Perl, but just the other day I heard that Perl is horrible and you shouldn't write anything in Perl. So I went back to the drawing board and wrote everything in Python. And there's all sorts of calculations here of how many atomic lookups in the deletions dictionary, the bloated dictionary that we created, are going to be required for this test to run, and how much time the test took, including, I'm going to say, including the generation of the actual gibberish to be tested. And you divide this by that, and you multiply this by that to see how long it's going to take to do the same feat that we tried to do before, which is to see how close to the dictionary a string of 8 characters is. Earlier it took us 2.5 days, and now by this calculation, it's going to take us a quarter of a second. A quarter of a second, that's an improvement by a factor of like nearly 1 million. So we're very happy now. And in the wise words of Hannah Montana, we can now enjoy the best of both worlds. The dictionary size is hefty, but it's not prohibitive. And our query time has improved by a really drastic amount. Okay, yes, we have this, limitation on the number of deletions that we can deal with, but I explained why I think it's a worthy trade-off. And this feature is now something that can actually happen in the real world. So we decided that now what we need to do is an experiment. So let's recap the 3 features that we decided to extract from pickups to see how close this pickup is to being DGA generated traffic. So there's the max number of DNS requests that got the same response, whether that's an IP address or an NX domain. For 10 of the involved requests, we calculated this feature that I just spent like 20 minutes explaining how it works, of how close this domain is to a concatenation of words from the dictionary. And for 10 of the involved requests, again, this was computed for 10 of the involved requests, just to improve performance. I think that's enough. And finally, we computed the frequency based on bigrams. I explained this feature earlier, mainly for comparison's sake, to see how our metric fares against this, and also they can work in unison to maybe detect jointly things that each one of them alone could not. So now we're going to see the resulting classifier classify a traffic capture. That's how this works. Okay. Now we're going to run this on a traffic capture. Now I set this log to basically pause the first 3 times something interesting happens, and then it's going to just blow past this, so we're not going to be standing here forever. Okay, we have the traffic capture, and we're starting to analyze it. And we're going to extract the features from it, obviously. Now we find that the most common DNS response that was received during this traffic capture is an X domain. So we're going to look at the requested domains that got this response, and now I bet you're getting a little suspicious looking at those domains. It's a list of 28 domains. And now we have our maximum domain collusion features. This is the maximum number of domains that mapped to the same response. Now we're looking at the longest because they're actually all the same length, so they're just sorted alphabetically actually, relevant requests, and we're going to start analyzing them using the features that we talked about before. Now we're going to start with what's called the pronunciation deviancy. That's just a fancy way of saying that we're going to look at the pairs of letters, the bigrams, and see how frequent they are, and how this compares to what we would expect from English. So we're going to start looking at the first domain name, and now the algorithm looks at this input, the domain name, and says, okay, it starts with C. How much am I surprised by the fact that it starts with C? Well, as you can see, the answer is 5.6 surprised, more or less. Don't ask me about the measurement units on this, because this is another whole talk about probability theory, and we don't have the time for that. The same happens now because after the C there's an I, and the algorithm asks itself, okay, I saw a C. How surprised am I by seeing an I after the C? Well, it's 4.3 surprised, less than before. And this goes on and on. Now we are looking at the I until finally we have a bag full of surprise, and we are very surprised. We have a number, and we normalize it by dividing by a factor of the length of the input, and we get a score of how surprised we are generally by bigram-wise, pairs of letters-wise, by this input, by this domain name. So we move on to the next domain name. The same thing happens. We get a general idea of how surprised we are by it. And then same for the next domain name. We went through 3 domain names, and now it's going to go whoosh. We went over all the domain names, and we averaged them out. And now we got a measure of how surprised we are by the bigrams, the pairs of letters, in all of the relevant domains here generally, on average. And the answer is 0.9 surprised. We keep on going, and now we're going to calculate the lexical deviancy, which is really just a fancy word for the feature that I spent 20 minutes explaining how we're going to put together, the closeness to a concatenation of words in the dictionary as approximated by a host of ugly hacks. So we're going to start calculating it, and in order to calculate it, the greedy algorithm is going to iterate over every possible prefix and see which prefix looks the most promising to take away from the input and say, okay, I imagine this more or less is my most promising candidate as something that used to be a word in the dictionary but got mutilated somehow. So we perform the lookup on the prefix C, and we can delete nothing and stay with C, or we can delete the C and stay with nothing. And it turns out that both of those options are in the dictionary. So obviously it's better to have to delete nothing and just say that C is in the dictionary. It's a candidate. We can just take it away and say, okay, that's a word from the dictionary. The downside, of course, is that C is just one letter, so it may be in the dictionary, but it may not be the best candidate to take away from the input because we want a longer candidate to cut the input length. This is how the greedy algorithm operates. It wants to take away the best candidate, and that also depends on the length. We want to make the input smaller as we work on it. Now we look at the prefix CI, and the same process happens basically with every prefix that is in this input until finally the algorithm makes the choice, okay, I think taking the first 2 letters, CI, is the best choice here. That's the closest thing I have here to a word in the dictionary that I can take away. Now the same thing happens again, and it takes away the prefix LI, and it takes away the prefix QI, and so forth, and so on, until finally it reaches a score for similarity to a concatenation of words in the dictionary for this domain name. Now we get the same calculation for the next domain name, and the next domain name, and the rest of the domain names, and they're all averaged out to find the final measure of the closeness to a concatenation of dictionary words of all the domains that were relevant, the 10 domains that we extracted and decided to take a look at. So we now have our final list of features. We have 28 domains pointing the same way. We have a lexical deviancy of 0.6 and a pronounceability deviancy of 0.9, where lexical deviancy, I remind you, is the feature that we built here, and the pronounceability deviancy is based on pairs of letters and how frequent they are. Now, the algorithm is going to be looking closely at those features, and it's going to look at the 28 domains pointing the same way and say, well, that's too much. 28 domains pointing the same way is really too much. Everything more than 5 raises alarms already. So it says that's excessive. Now, as for the closeness to a concatenation of words in the dictionary, it looks at the value. Later, I'm going to tell you where the parameters for the classifier came from. It looks at it and says that's also excessive. It's not close to concatenations of words in the dictionary at all. And finally, it's going to look at the pronunciation dependency, how likely the pairs of letters that appeared seem to be. And it's going to say that it's actually reasonable, because we got the value of 0.9, and anything up to 1.5 is actually reasonable. So lots of domains, they look like gibberish to our feature, but the bigram feature looked at this thing and said, well, okay, seems fine. Why is this? I imagine some of you have guessed, it's Quaijibo. This pickup was generated by Quaijibo. So now this classifier is going to look at the domain collusion and lexical dependency and pronunciability dependency and say, okay, Mr. Pronunciability dependency, you said that this was reasonable, but I have another feature now that I can rely on, and this is definitely DGA. So this was the short demo of how this thing works. And now we're going to look at some pretty graphs. Now, we took 10,000 pickups out of Checkpoint's malware lab just to see how the data looks if we map it across the features that we have created. And these are your 10,000 pickups mapped across the closeness to concatenation of dictionary words and the maximum domain name collusions, the number of DNS requests that got the same response. Now, if the lump there to the upper right seems suspicious to you, then you're probably right. Because when we took some test samples, like 100 test samples, just to test the waters, and we labeled them by hand, the DGA samples were in the lump, and all the clean samples aligned neatly across the vertical over there to the left. And if you want a visualization of the classifier itself, that I promised you that I'm going to tell you how it was generated. Actually, I tried all sorts of machine learning algorithms. I tried Gaussian mixture models and also that, but so far I got the best result by just looking at the test data myself. So really, this is a case of machine learning, a subclass called Ben learning. And I'm kind of bummed because I really wanted a proper machine learning algorithm to make sense of this data, and I'm still looking for it. This is a classifier. It was not generated based on any of the data that you see most against the classifier. That's the test data. I mean, it's the 10,000 pickups that we took. I generated the parameters that generate this classifier based on other traffic captures, of course. You don't test your classifier based on the same samples that you used to generate the classifier. Then you're going to have overfitting, and that's not cool. This is how the classifier looks. And now I'm going to talk a bit about the future of this project and what needs to be done further on it. Now, first of all, more testing, because testing on 100 samples is nice, but I bet that there's a lot of surprises that DGAs have up their sleeves that will require this project to evolve and get better features and fine-tune the features to be better. Actually, we're going to touch on one of those in like 2 slides. Next, as I said, more machine learning. I want to be using an actual machine learning algorithm, even though this finely tuned by hand classifiers worked very nicely. I think you saw the graph, you saw that it was a very reasonable conclusion to draw from the data. And finally, there's Gibberish Detection 103. Because as it turns out, domain generation algorithms, some of those at least, have already anticipated this kind of analysis that we have performed here. And you have DGAs such as the one used by the MATS new malware that generates random domains by concatenating words from the dictionary. So the bigram feature and our features is going to do nothing to detect this kind of DGA. How could we evolve to defeat this? Well, I'm just throwing an idea out there. Maybe we could take a look at the words from the dictionary that we actually found and make some kind of semantic comparison to see how likely they were to actually appear together in the same domain name. I mean, panther and asphyxiation. I guess I could see it. A good name for a rock band. So how about undetectable gibberish? Can this arms race eventually end in undetectable gibberish? Well, my personal opinion is that an undetectable lump of gibberish is a contradiction in terms, because the idea with undetectable is that it resembles the legitimate distribution of what you expect to see in the real world across every conceivable feature. Now, if something resembles the real world across every conceivable feature, it's not going to look like gibberish to you. But that doesn't mean that we're off the hook, because while I think that undetectable gibberish is an impossibility, undetectable auto-generated domain names are very much a possibility. I think that in theory, DGA authors could eventually create an algorithm that generates random domain names that are very much like domains that you see out there in the real world across every feature that you could conceive of. And it's not going to run into any issues, because even if you put that set of constraints, eventually it's going to be the space of possible domains is so large, even with all those constraints, that there's plenty of space there for auto-generated domains to prosper and flourish. But, you know, that's all theoretical and in the future. In practice, you have the total gibberish DGAs running amok today. You have Quigibber running amok today. And at the top end of the hierarchy, you have the dictionary concatenation-based DGAs running amok today. You know what? Let's first force all the DGAs to actually use undetectable gibberish. And if we do that, I believe that we will have done enough for that day. Yes, then we can think what we can do from that point on. Now, your next question regarding this nice classifier that tells you whether traffic captures are containing DGA or not is, can I have it? The answer is yes. There's the address of the GitHub repo. I really hope that people try to use it and say, oh my God, Ben, it doesn't work for me at all, and it's useless. Please improve it, because I want to improve it. I want this thing to work and be available for anyone who wants to detect DGAs in their pickups. So we can now summarize this whole journey. We can say that DGAs are a pain, and that automatic detection of DGA helps. But if it is done naively, it gets confused by strategic placement of vowels. But if you do it less naively, it gets less confused by strategic placement of vowels, and it becomes equipped to handle funny domain names like Tumblr. And undetectable auto-generated domain names may be a possibility in the future, but you know what? First, let's force all the DGAs to use them, and then we can see what we can do then next. So thank you, and are there any questions?
Okay, thank you too, Ben, for your very nice talk, very interesting talk. If you have to leave now, do so quietly, please, so we can have a nice and informative Q&A session. Thank you very much. So we have a few minutes of time, not so few minutes, we have a lot of time for Q&A. So if you have any questions, line up at the microphones, and we will also take questions from the internet. So leaving is okay, talking is not, unless you step up to a microphone. Thank you. So we will start at the front, from my side left, from your side right microphone.
Hi, so thanks for your talk. I was wondering, you had lots of issues with the dictionary because of its size and so on. And then you built all these hacks, but I wondered whether you thought about getting rid of the dictionary altogether by including syllable information, for example, because I also think you're rather interested in possible words of the English language than the words that are listed in the dictionary. So, for example, Mandalorian or something like that is probably in a dictionary about Star Wars, but probably not in the dictionary used. But it is a possible word of the English language by the rules for the syllables. So yes, I just thought maybe you could get rid of the dictionary by using more syllable information.
So, well, actually there has been one paper on this subject that used exactly the approach that you described, well, more or less, by stemming words and trying to look at more themes and so forth and so on. It was very interesting. Their particular attempt didn't go so well, but I think it's a good approach. I don't know about getting rid of the dictionary completely, because I'm not very convinced about how the word stems or the syllables or the atoms that you are proposing are going to be at reconstructing words from the dictionary. But you know what? I think it's an avenue worth pursuing if actually this could help downsize the dictionary, then it's something that I'm interested in looking into and doing, because right now the dictionary weighs like 10.7 gigabytes, and anything to make it smaller is very welcome. So thank you.
Okay, the left front microphone, please.
I was wondering how you manage domains like XKCD or things which are valid but which aren't in the dictionary.
Things that are, you mean like XKCD because it's not even like a word in the dictionary at all? Yeah, no, that's a really good question. You're not every domain name is going to fit into this paradigm of domain names that are like a word in the dictionary, which is why this thing still needs to be tuned, and more approaches for recognizing valid domain names need to be added to it. Looking at the top domains, I mean, that's a given. You see, let me ask you a question. What sort of approach do you see that would have foreseen from first principles that XKCD is a legitimate domain name? That's kind of an issue. So I think if things like XKCD, they will either have to be manually whitelisted, or you could have a specific, I don't know. I really don't know how you could see in advance that XKCD is legitimate, except, you know, taking this a priori knowledge and applying it.
Okay, the rear right microphone, please.
I just wanted to follow up on that a little bit more. How are you dealing with Punycode domains, as well as some domains that are used in other countries that look like English letter gibberish? China uses a lot of strings that we wouldn't necessarily recognize. And have you looked at other properties of these domains, such as time of first use? You know, has anyone gone to these domains before, as well as how more recent are they registered?
Okay, so first of all, regarding the languages issue, this project was specifically about English. It is a work in progress and a proof of concept. I specifically thought about that. And if this thing is actually going to be used and is going to function properly, I am interested in expanding it to be able to handle other languages. Now, can you remind me of your other question?
So, yeah, Punycode or domain strings that are English characters but are used in countries, or popular in countries that it's not English words.
That's what I said in response to the first question.
Other characteristics of these domains, for instance, have they ever been queried,
yes.
as
Access,
well as,
right.
you know,
right.
are they recently registered?
Yeah, I remember now. Well, plenty of projects trying to solve this problem in the past have relied on this sort of thing, keeping a sort of ongoing intelligence operation that will be able to tell you whether the domain is DGA or even in generally suspicious based on this sort of intelligence. When was it registered? When was it accessed? And so forth and so on. These are all very useful features. I specifically decided that they were out of scope for this project, and this project should join hands with any sort of engine making use of an ongoing intelligence operation instead of reinventing the wheel and re-implementing that sort of approach.
Thank you.
Okay, Signal Angel, are there questions from the internet?
I'm just looking at them right now, but it seems the internet had the same question as the microphone here.
That's convenient. So, okay, the next question from microphone right front.
Thank you for a good presentation. It sounds like the DGA algorithms will soon output some sort of dadaistic poetry that will make your system have to identify dadaistic poetry, but also in like 400 different languages, such as the .com zone will allow you to register it. That will be a problem. So my question is, in what place in the DNS ecosystem do you believe that your system will have, I mean, where exactly do we have a use for this?
Okay, so actually, this was conceived in an entirely different context than what I described in the first few slides. This was conceived as a feature that you can compute on a sample in a sandboxing context. So you can do machine learning operations and so forth and extract a feature you can look at the sample and say, okay, it's DGA. That's one of the features that I can look at and use. But as I mentioned in one of the first slides, I think that the pinnacle of what this thing could do is if the code were optimized for performance in that kind of context, which it currently is not. It could sit on a firewall and throttle DGA traffic before it manages to get out of the network.
Thank you.
Okay, and there's another question on the rear right microphone.
Yes, you mentioned that you tried other machine learning models for this. Did you try a Markov chain classifier?
Actually, that one I haven't tried. Markov chains, you're saying? Okay, I'm going to try that tomorrow.
I'm aware of some other research that does DGA classification using Markov chains, and there's a couple advantages to this. So if you're concerned about bigrams not being enough, you can extend it to a third order or a fourth order Markov chain assumption with smoothing, and you can also, lookup time is linear, so it's pretty fast.
Okay, I'm going to have to take a look at that. Yeah. Thank you.
Okay, on the left rear microphone, there's another question.
Yeah, hi. Did you try using Bloom filters for the lookups? Because they might reduce the lookup time significantly.
To use what?
Bloom filters.
Bloom filters? No, I have not. I look into that too. Lots of useful suggestions today, I see. I had hope for that.
Okay. We have time for another couple of questions. So I'm looking at the Signal Angel, nothing from the internet. Okay, last question, maybe to wrap it up from the right front microphone.
Thank you. I liked your presentation very much. I'm more from the data science and not so experienced with the network perspective.
Okay.
I think it looks like a cat and mouse game, and I think from the methods perspective, I think it's a losing game. So I would like to hear more about the motivation at the beginning. The standard process that is described, how it is handled with the middle management and the reports that is written and the reverse engineering. Are there statistical methods involved too today that are the same cat and mouse game and you are only playing it better? Or is it just this game, which I believe personally is a losing game?
I agree with you completely. That's what I said. In theory, it really is a losing game because authors of DGAs are going to evolve eventually. They have and they will. And as I said, my personal analysis, and it seems that you agree with me, is that eventually, theoretically, they win this game. Now, security is full of such games where the attackers theoretically eventually win because the mission, the burden on the shoulders of the defenders is like some, eventually, in the worst case, in worst theoretical case, it's equivalent to some NP-complete problem, or it's generally, in theory, in the worst case, impossible. But while you are correct, I believe that we should be focusing on what's happening right now. As I said, okay, it's a losing game right now, but besides trying to look aside and think, okay, what game changer can we bring in here to make this ultimately not a losing game, we need to do our best to push forward and make it less of a losing game temporarily, even if eventually we know that in theory we're going to lose. That's what I believe.
Okay, then the rest is give a warm applause to Ben, and thank you very much for your talk.
Thank you.